DCMHS, the top that you can share with us since we have a little bit more time. There will be another session today on DCMHS overview, but since we have some time, maybe we can take advantage of that.
As CMX said, right, so from a DCMHS workgroup perspective, different processor vendors along with different OEMs and inputs from ODMs, we're taking that in and looking at how to provide that flexibility, to our end customers, whether they wanted to move from, say, Intel to AMD, AMD to Ampere, and vice versa, right? Being able to do that from a security perspective, there are a lot of BMCs out in the market. There are different security implementations, and really there are different philosophies on what entails and how much security folks want to implement on the platform. And so through this discussion and convergence around the specification, whether it's the evolution of DC SCM to DC SCM 2.0, or looking at what the acceleration needs are going to be and how the OCP module is going to evolve. So looking at the baseboard, looking at the security piece, looking at the networking and acceleration piece, along with there are other efforts for power supply and also interconnect manageability links and protocol. So once all of that comes together, I think that's going to provide a really options for end customers and flexibility in the ecosystem.
Very good. Thank you very much. Appreciate it. Next, we will have a presentation by another subgroup within the server project, Open Accelerator Infrastructure, OAI. As I shared with you earlier, server project runs with multiple active subgroups. One of the subgroups is the Open Accelerator Infrastructure. We have a presentation on that today. Other subgroups include NIC3, used to be called MES, that's a networking solution, HPC, ODSA, which is based on specifications for die-to-die interconnects. And there are other work streams within server project, for example, SIOV and extended or external cabling systems. And one central around composability is composable memory systems around CXL connected memory. So those are the subgroups that are active within the server project. Please join, make your contributions. Today, we will dedicate a little bit more time to OAI. Please go ahead, introduce yourselves and the topic.
Okay, thank you, Samak. Hope everyone is having a great second day at OCP Prague. My name is Vasanta Madduri. I'm with Broadcom, and with me is Samuel Kocsis from Amphenol. Like Samak said, OAI is a subgroup workstream within the OCP. And this workstream, within the workstream, Songkok, who's a OAI co-lead, co-chair, is not here, so we'll give an OAI timeline update about the spec. And then our key focus today is there is a challenge in the OAI subsystem as ODM vendors start building this to actually deliver systems at 112 gigabits per second, which is part of the spec. So we, as OAI Workstream members, contributed components to this validation, and we are going to present our validation results. Agenda today is simple. First, an update on the OAI spec. Then we'll talk about some of the system components, which are, again, the focus is on 112 gig. And then we'll talk about how we came up with the demo concept, the various components which enable this demo, and our validation results for the link. The OAI timeline itself, it started way before, I as Broadcom joined this, started in Q4 of 2018 as a concept. But the real focus for the last 6 months was on the OAM 2.0 and the UBB 2.0 specs. And both of these were submitted to the OCP Incubation Committee a few weeks ago, and it was approved. And the general OCP community should see this spec in the next couple of weeks. The next focus of the OAI workstream is going to be the UBB tray spec, and I will show what are the components. So one of the components of the OAI system is the UBB tray, the UBB tray spec, and also the expansion module spec. These are the two that the workstream will work on with a goal to release these specs by Q3 of 2023. Shout out to all the various workstream members. More are joining, and especially if in the next few quarters, if you're interested in the expansion spec or the UBB tray spec, so we encourage you to join the OAI workstream. So now looking at the OAI system blocks, once you look at the spec, there are many components defined as the OAM system building blocks. But the key ones today for this presentation that Sam and I are doing is the UBB, which is the Universal Baseboard, which is the backplane. And there are 8 OAM modules which go onto the UBB, and then 8 expansion modules. And again, the spec is done very flexibly, basically in terms of rates and in terms of these topologies. It's defined with 8 OAM and 8 expansion cards, but I just want to also let you know there's an option in the spec to not have the expansion cards and have a smaller card, UBB card. So to enable UBB at 112 gigabits per second, the OAM itself connects to the UBB with a connector, high-speed connector, and at 112 gigabits per second LR channel is what is defined. And the expansion card again has high-speed connectors, 2 high-speed connectors. And on the expansion card, you could have a retimer or a crossbar or a switch. There will be 4 OSFP cages for scale out. So the 2 topologies which are of challenge that we studied for validations are the end-to-end channel for expansion to expansion, and we also looked at expansion to OAM. So the expansion to expansion use case, what the main use case is when you have multiple OAI systems sitting in the racks, and they need to scale out to interconnect. In that case, the expansion to expansion use case comes in. So the OAI spec has defined the laws for this use case. And at the bottom here, you can see the expansion. And again, this is in both directions, TX and RX, both directions, bidirectional. So we have defined a loss budget on the expansion card at both ends and the I/O channel connecting. For end-to-end channel assessment, for the other use case that we looked at, which is challenging, is for OAM to OAM connection, when the workloads have to be shared between the OAMs to improve the AI training times. You've been hearing about that from various speakers about how the AI training times needs to be reduced. And in this case, basically, again, the OAI spec has defined the PCB channel basically from expansion card, then basically it goes across the UBB trace, and two high-speed connectors, one going from the expansion card to the UBB backplane, which is the Molex MES Pro connector, which has been contributed for this study. And the other connector, which from Amphenol, is their high-speed connector XMAX 2, and that one is connecting to the OEM module. On the OEM, there is a little more loss defined because of that package, more than for the expansion card. There's 8 dB of loss. So concept to demo, we started in Jan of 2022. Last year on doing this, we simulated. We got the simulations for all the components done. We validated that. We presented that at last OCP Global, and now we actually have results with the real hardware. And the goal is at OCP Global Summit to actually have a live working OCP system, or OAI system. So the components, in terms of from Broadcom, we have a high-speed retimer. It is a lead LR retimer which can compensate loss for long channels, 45 dB. It can be used for scale-out as a 16 by 16 retimer, or it can be also used for OEM connections configured as a crossbar. Complies to the IEEE specs, Ethernet specs, CI 112 gig compliant. And it also has a KP4 FEC for error connection. Key to these AI systems is latency. So we have low latency, and also latency variation is important. More than that is a very low in ours. And then the power has to meet to a spec which has been defined by the OAI subsystem. Another contributor component which was used in the study is the Molex MES Pro connector. This is pin-to-pin. It is compatible with the previous mirror MES connector. It has a stubless contact for a low cost. It is also qualified for 112 gig bits per second and PCIe Gen 5, Gen 6.
Thanks, Vasanta. There were some residual animations there. So this Mirrormez Pro is from the Molex family of products. And the 90 ohm impedance is really helpful in making the form factor suitable for both PCIe as well as Ethernet-based protocol. The XMX2 solution is the PCB connector that makes the connection from the UBB to the expansion module. It's more of a traditional backplane connector with a vertical header and a right angle receptacle. This is a solution that sort of adapts and is a superior maybe implementation of the card edge connectors that are used in add-in cards and host board adapters today. It provides a very robust mechanical interface as well as the optimal signal integrity. And this also is available in 90 ohms, which helps support the flexibility to support PCIe as well as Ethernet-based protocol. On the I/O side, the OSFP 800 is an industry standard multi-vendor pluggable I/O solution defined by the OSFP MSA. It's an 8-lane form factor, and one of the unique features about this form factor, the picture on the right side of the screen shows the integrated heatsink. The OSFP module is available with and without the integrated heatsink, but the integrated heatsink is what helps provide thermal management capabilities up to 33 watts. Now that power consumption is really designed to support optical transceivers. Most of the expansion module architectures are going to be taking advantage of the copper-based solution. So the form factor itself could support both integrated heatsink or riding heatsink version. And again, this is an industry standard interface to be used. As Vasanta mentioned, at the OCP Global Summit last fall, we presented simulation results for this topology. This was the OAM to expansion module link using the components we just described. The channel goes from the Broadcom retimer through the OAM traces in the Mirama's Pro connector, through a length of PCB trace on the UBB, and into the expansion module via the Amphenol XMX2. So this simulation model, the end-to-end, the die-to-die channel was about 35 dB. And you can see we've used prefect BER as well as signal-to-noise ratio margin, which is effectively the measured signal-to-noise ratio compared to the minimum signal-to-noise ratio needed to achieve a locked link. So this was the first step in promoting confidence that we had a solution space for this architecture. This time around, we want to do the same thing, but try to capture some measured results. So these are the fixtures that we used from the various contributors to link together the topologies representative of what you'd see in a real system. The one addition is the channel emulator board from Multilane. This provided a proxy for the UBB traces that would exist, allowing us to pick different lengths and tune the different lengths that we'd see going from OAM to OAM as well as OAM to expansion module. Multilane has been a great contributor and partner in the OCP community and really a leader in the test and measurement space, so we appreciate their support here. So the first link that we looked at and tried to replicate by connecting these fixtures together was the expansion module to expansion module. This is an external I/O cable connected between two OSFP ports. The OSFP MCBs actually act as a pretty good proxy for the physical routing that you'd see on an expansion module between the retimer and the OSFP port. Between the OSFP ports, you could use any flavor of OCP or OSFP cable, active cable, optical transceiver. But the way that the expansion module is kind of constructed, it would really be ideal to take advantage of the passive copper links. So what we did here was used a 3-meter passive copper cable to try to push the insertion loss budget towards that 35 dB mark. Here's some measured results of the passive interconnect. So this is a measurement of the cable assembly mated with MCBs on either end. In the Ethernet world, this is referred to as a TP1 to TP4 measurement. The spec for 112 gig per second per lane requirements is 19.75 dB at 26.5 gigahertz, which sort of works out to the 2-meter cable assembly reach that you get at 100 gig per lane. This cable, again, being 3-meter, we're measuring closer to 23 or 24 dB. But that 3-meter reach allows for the flexibility to get all of the intra-rack cabling that you need to connect these boxes together. So 3 meters was sort of a critical threshold that we were looking at. So we connected all of these together with the additional cabling and the fixture loss themselves. The die-to-die loss here for this link was about 37 dB. And we captured the results both for a through path without crosstalk, and then we added dominant aggressors near end and far end from the OSFP port. And you can see here the results are a very good, significant margin compared to the simulation results. There was a little bit of miscoordination with the fixtures to try to get the OAM to OAM and OAM to expansion module links measured. But what we found was the XMX2 fixture, in terms of loss between the reference planes, was a pretty good proxy for the Mirama's Pro. So we constructed the channel with the Broadcom retimer going through an XMX2 connector through the Multilane ISI board, and then through the XMX2 connector again to replicate that OAM to OAM or OAM to expansion module link. In this case, because we were going back between the XMX connector twice, we weren't able to capture all the crosstalk, but the through path by itself shows significant BER and SNR margin compared to both the expansion module to expansion module links as well as the simulated results. So I'd love to stand up here and say that was due to the contributions from Vasanta and my company, but in reality, the test fixtures themselves are usually optimized to highlight the best performance of these products. The actual implementation, the PCBs used in the UBB, the OAM, the expansion module are going to require thicker paddle cards, more complex construction. And the test fixtures themselves sort of spread out the discontinuities that you'd see in that signal path. So while this is impressive, we really want to get to a point where we're able to demonstrate this in a real system. And as Vasanta mentioned, that's our target for the summit, just 6 months away in October. So our call to action is really for anybody who's interested in deploying and implementing these system solutions to help get involved and help us get to the release of these specifications and ultimately bring these hardware products, this powerful accelerator and networking solution to the broad market. So, thank you.
Very good job. Another good example of how open community within OCP works.